Hello, welcome back. This is Brad Stribig, and I'm going to discuss Chapter 2, Part 2, in particular, the relationship between mass of a compound, its density, and concentration. This can be a little bit confusing because density and concentration have similar units. Density is how much an individual molecule weighs. So the density of pure H2O with nothing else in it is 1.00 grams per milliliter at standard conditions. However, we can have various concentrations of compounds in water, such as dissolved sodium in water, which could be 10,000 or 10 grams per liter in water. So we have similar sounding units for density and concentration. Density is the mass per volume of the pure substance, whereas the concentration is usually what we're concerned about for the pollutants or impurities of a substance or other compounds within the bulk solution, whether it be water, air, or even a solid volume. So for example, if we have 55 moles of distilled water in a 1 liter Nalgene bottle at standard temperature and pressure, we can determine the density of the fluid. We'll do this for grams per liter, and you can convert those units to kilograms per meter cubed or pound per foot cubed. We know how many moles now are in a given liter, so we have to find the molecular weight of water. This is fairly straightforward. To find the molecular weight of a molecule, different elements bound together, we take the molecular weight of each element. Hydrogen has a molecular weight of 1 gram per mole, and we multiply by the number of moles. So there are 2 grams per mole of water of hydrogen, and 1 gram, which is 1 mole, which is 16 grams per mole. So 16 grams per mole of oxygen in the molecule of water. So the total water molecule has a molecular weight of 18 grams per mole. We've been told there are 55 moles per liter, so we multiply that by the molecular weight. The units of moles cross out, and we're left with the number of grams per liter, and we find that there are 1,000 grams of water in a given liter of water, and that's going to be the density of the bulk solution of water is about 1,000 grams per liter, or 1 gram per milliliter. As mentioned, for concentration, most compounds in the environment are mixtures. For instance, what we think of as pure drinking water isn't H2O, but it can have dissolved gases in it, dissolved ions, and dissolved minerals, which give the water from one place to another a different taste. So if you've ever gone on vacation and thought, geez, this water tastes awful, it's because you've grown accustomed to the dissolved minerals, gases, and salts that are in the drinking water where you live, and there are different concentrations of those same dissolved minerals and gases in drinking water in other places because the Earth's mineral composition is different from place to place. This doesn't make the water unsafe, it just means it has a different concentration of various minerals dissolved in it. But most of the time we're concerned about what the concentration of these chemicals are in water, because in some instances we can have pollutants or even naturally occurring compounds like certain elements of arsenic or water in some areas of the world where those levels can be too high and are improper. We can also be concerned about things that are too low for life to exist. For example, if the level of dissolved oxygen in water, so the dissolved gas oxygen in water, isn't high enough, fish won't be able to breathe and then will die. And that's a problem we'll discuss in great significance in Chapter 4. The mass of pollutants is typically very small, as we've shown in our previous calculations in Lecture 1 of this chapter. For example, if the total mass of a sample is 1,000 grams or 1 kilogram, the mass of the pollutant, if it's 1%, is only going to be 10 grams. When we talk about parts per million of something, we're often talking about things on the order of 1 milligram per kilogram. So a 6-order differentiation in the mass of a given compound or pollutant in the environment. Water has a specific density, as we've shown, of 1 gram per milliliter or 1 gram per cubic centimeter. Another way of saying that is that there are 1,000,000 cubic centimeters per 1,000 liter, or 1 meter cubed. The mass density of a substance in water is related to the volume fraction by the specific density of the water itself. What does this mean? So, if we have 1 gram of water, that's equivalent to 1 cubic centimeter. So if we have 1 microgram of a pollutant, 10 to the 6 orders of magnitude less than a gram, per 1 gram of water, that would be the same as saying that we have 1 microgram of that pollutant in 1 cubic centimeter of water. A cubic centimeter has the same volume by definition of 1 milliliter. So that also gives us 1 microgram of a pollutant in water per milliliter. If we have 1,000 milliliters, we would multiply the denominator by 1,000, and to get the same unit conversion, we'd multiply the numerator by 1,000, so that gives us a value of 1 milligram per liter. This is often what we mean when we refer to 1 part per million by mass in the aqueous phase, that 1 milligram per liter is equal to 1 part per million by mass. We will note with significance that it's much different in the gas phase because the density of air is much different. Let's try an example. If we look at calcium from dissolved limestone in the environment and other minerals, is often a common component of fresh water. If we have 1 liter of a solution and it contains 0.1 grams of calcium, we want to find the calcium in the following units. Let's start first by finding the concentration of calcium in grams per liter of water. So we're given that we have 0.1 grams of calcium, and we're told that that's in 1 liter. So the value is pretty simple. 0.1 gram of calcium, the dissolved form of the calcium is Ca plus 2, per liter of water. If we want to find the mass fraction for that compound, we take that same 0.100 grams of calcium. This is a mass per volume, so we have to multiply by the mass of water in that volume of water, and that would give us a value of 0.0001 grams of calcium per individual gram of water. And here we've boxed the solution, so we have a very small mass fraction. If we take that mass fraction and convert it to a percentage value, we simply multiply by 100%. So we have our mass fraction, 0.0001 grams of calcium per gram of water. If we want to express that in mass percent, we have 0.01% calcium by weight of water. The percentage calculation is similar to that of parts per million. For a percent, we multiply by 100 to basically write less decimals and express small fractions of something. We can do the same thing for a part per million, where the fractional value is not 1/100th of something, but 1/1,000,000th of something. Let's show what we mean in this example. So if we have that same mass fraction, 0.0001 grams of calcium per grams of water, and we want to find the concentration in parts per million, we multiply by 1 million, 1 part per million, and that will give us a part per million on a weight basis. Multiplying 0.0001 by 10 to the 6, or 1 million, gives us 100 parts per million of calcium by weight, which is the same as what we've discussed earlier in terms of grams per liter, the mass fraction, and the mass percentage. These are all the same numerical fractions, just different ways of expressing the units. Finally, let's look at this in terms of milligrams per liter. If we have 0.100 grams of calcium per liter, we simply multiply by the conversion factor of milligrams per gram for the calcium, and we get 100 milligrams of calcium per liter of water. Notice how this relates to the previous discussion that we had, that 1 milligram per liter of something is equivalent to 1 part per million weight of a substance in water, or fresh water. So we also have a concentration of 100 parts per million of calcium by weight. So your units of concentration can be expressed in any of these values. grams per liter, a mass fraction, a mass percent, parts per million, or milligrams per liter. Knowing how to go back and forth between these things is the type of thing that engineers get paid to do an awful lot of the time. This may not be the most exciting math you've ever encountered in your collegiate career, but it is something that's a common practice of engineering. It's fundamental to what we do, and you'll get to practice it a lot through this textbook. Thank you, and in the next section we'll go on to talk about how molecules divide in different places, or what their fate is in the environment.